Assalamualaikum and good morning everyone. Today our group will present our case study on deep foundation system in Kuala Lumpur, focused on two construction projects which is Merdeka 118 and Bukit Bintang City Centre or BBCC. These are the members of our group. First is Muhammad Haziq Zafran, next is Muhammad Fawaz, next Muhammad Akil Nakiuddin, next is myself, Wan Muhammad Taufiq Hidayah, and lastly, Muhammad Amar. Our first case study is Merdeka 118, which is located in Kuala Lumpur near Stadium Merdeka. The building stands at 678.9 meter with 118 floor. The project was developed by PNB Merdeka Venture and took approximately 9 years to complete from 2014 until 2023. Because of its extraordinary height, the project required a highly sophisticated deep foundation system to safely transfer the building loads into the underlying limestone bedrock. Several organizations play important role in this project. The developer was PNB Merdeka Venture. The architecture design was prepared by vendor Katsladitis GDP Architect. The quantity surveyor was Langdon and C, while Turner and Townsend act as the project manager. For construction, the main contractor was Samsung City Corporation together with Pintaras Jaya Berhad as piling subcontractor. The geotechnical engineering work were carried out by Arup Geotechnic, while Thornton, Tomasetti, and Mainhard were responsible for the structural engineering design. The collaboration is unique for the deep foundation system. One of the biggest challenges at Merdeka 118 was the ground condition. The upper layer consists of quaternary alluvium and Canary Hill residual soils, while beneath it lies the Kuala Lumpur limestone formation. This limestone is highly irregular due to karst formations which contain underground cavities, voids and solution channel. In addition, the rockhead depth varies significantly, range from about 10 meter to more than 80 meter. Groundwater was also encountered at 3 meter to 5 meter below ground level. This challenging geological condition require detailed site investigation to be constructed safely.
Next is design consideration. Before construction began, engineer preferred study the site condition and structural requirement. Since Merdeka 118 is 678 meters tall, their foundation had to support a massive structural load of around 300,000 kilonewtons. One of the biggest challenges was the karst limestone beneath the site, which contains underground cavities and weak zones. To overcome this, engineer carried out 100% pre-grouting by injecting cement rock into the ground before piling works began. Another important consideration was the nearby heritage building, located only 30 to 50 meters away. Therefore, vibration and ground settlement were closely monitored throughout the construction to prevent any damages. Next is construction method. The foundation construction was carried out in 3 stages. First, engineer improved the ground by drilling investigation holes and injecting rock into limestone cavities to strengthen the soil. Next, bore piles were drilled deep into the limestone bedrock using large rotary drilling rigs. These piles were circuited into the rock to provide strong support for the building. Finally, reinforcement cage were installed. Concrete was poured using the Trimat method, and large reinforcement concrete raft was constructed to system all piles into the strong foundation system. Next is material use. High quality materials were used to ensure the strength and durability of the foundation. The low pile were constructed using grade C40-50 self-compacting Trimat concrete which flow easily into deep piles and provide high strength. The ground foundation used grade C35 to C40 grade mixed with 50% ground granulate blast furnace slag or GGBFS to reduce leak during concrete curing and minimize cracking. In addition, grade 500 reinforcement steel, bentonite slurry and steel casing were used to strengthen the foundation and stabilize the borehole during digging. Next is equipment and machinery. Several advanced machines were used during the construction. Large rotating drilling rig drilled the bore piles deep into limestone, while down the hole drilling rig straight strong rock socket. Crawler crane lift the replacement cage and steel casing into place. The high capacity concrete pumps delivered concrete continuously during the pile construction. A betonet recycling system were also used to clean and reuse the drilling slurry, improving the efficiency and reducing waste. Next is testing and quality control. Strict quality control was carried out throughout the project. Each pile underwent pile integrity testing to detect cracks or defects, while cross-hole sonic logging checked the quality of the concrete sinks. The engineer also performed obstacle cell load tests to confirm that the piles could safely support the building design load. In addition, the quality of granite, slurry, concrete temperature, and ground movement were continuously monitored to ensure the foundation met all safety and performance requirements.
Hi, my name is Muhammad Fauzi Makmur. Now, let's look at how well the foundation actually performs. Put simply, it was a 100% success. Every single pile meets its weight requirements, and we had zero failure on site. Our testing proved that the rock grid was incredibly strong, and testing the underground cavity beforehand worked perfectly. Means we used far less grout later on. Most importantly, the grout did not sink or shift unexpectedly, so there is absolutely zero damage to the structure. Next, building on this kind of unpredictable cave-fill ground is not cheap. The total foundation cost came to between 315 and 415 million ringgit, which is about to 8 to 12% of the entire project budget. This includes the cost of drilling deep into the ground and building a massive reinforced concrete base. While these numbers are high, they were completely necessary. Standard pile will not work here. For a lower restore, the foundation is our ultimate insurance policy. Failure was simply not an option. Next, of course, a project this big comes with a great challenge. We run into three main issues. First, hard rock was bending our drill bits. We fixed this by switching to specialized rock cutting bits and pre-drilling smaller pilot hole. Second, the heavy concrete was pushing the steel cage upwards. We solved this by using heavy physical frame to hold the steel down and monitoring it in real time. Third, we had to stop the massive concrete base from cracking due to heat. We used ice instead of water in the concrete mix, and it can cooling pipes through it to keep the temperature down. Looking ahead, we recommend 3 smart upgrades for future projects. First, automated drilling. Use smart drill that track speed and pressure in real time to instantly spot underground cave. Second, 3D ground modeling. Updates our digital maps live as well as we drill, so we know exactly where to pump the concrete. Third, live tracking. Use automated sensor to monitor ground movement in real time. This let the team instantly and protect nearby historic building.
Okay, thank you, Fawaz. Now I will explain about precision under pressure. The BBCC project was built in a very busy urban area with limited working space and complex ground conditions. Therefore, engineers need to work with high precision and careful planning to ensure safety and accuracy. Advanced technology, continuous monitoring, and experienced workers were important to avoid damage to nearby buildings and infrastructure. Net is incurring an 8.7 billion ringgit urban behemoth. The BBCC project is a Dutch development project. It was built on the former Pudu Prison site. The project includes residential towers, commercial buildings, and public transport connection. Many parties were involved in this project, such as developers, contractors, and engineers. They worked together to choose the best foundation system for the project. Next is subterraneous battlefield. One of the biggest challenges in this project was the underground condition. The site has granite soil, limestone rock, and nearby MRT tunnels. This condition can cause problems during construction. Because of this, engineers had to carry out detailed soil investigation. This helped them to understand the ground condition and choose the correct foundation system. Next is engineering for extreme, which is load versus proximity. The engineers had to deal with two main challenges. First, the buildings have very heavy load, so the foundation must be very strong. Second, the construction site is very close to existing structure and MRT tunnels. Therefore, the construction work had to be done carefully to avoid damage. Proper planning and engineering solutions were very important in this project. Next is the subsurface choreography. The construction of the deep foundation involves several steps. First, the engineers carry out site investigation and soil testing. Next, they start the reading work and install the reinforcement cage. After that, the concrete was poured into the foundation. Finally, quality inspection and monitoring were carried out to ensure the foundation was safe and strong. Next is the engineer arsenal, which is machinery and materials. In this project, many types of machinery and materials were used. The main equipment include drilling machine, crane, and monitoring instrument. High-strength concrete and steel reinforcement were also used to increase the strength and durability of the foundation. The use of modern technology and quality materials helped ensure the success of the BBCC project.
Thank you, Haziq Zafran. Now I would like to present on quality control, testing, and monitoring methods used to ensure the safety and reliability of the piling works. Firstly, static load capacity testing is carried out on selected preliminary piles to verify that the piles can safely support the design loads and to determine the appropriate pile capacity based on the ground condition. Next, dynamic integrity testing is conducted after pile installation. High-strength dynamic tests are performed on selected production pile, while low-strength integrity tests are carried out on all installed piles to detect any defect or damage. To ensure concrete quality, strict material quality control is implemented. Fresh concrete is checked through slump flow and temperature tests, while cube strength tests are conducted to confirm that the concrete meets the required design and strength. Finally, real-time telemetry monitoring is used, especially in areas near the MRT. Automated monitoring station continuously measure ground and structure movement and send data to the project team at regular intervals. This allows any unusual movement to be detected early and help maintain construction safety. Overall, this testing and monitoring system ensure that the piling works meet quality standard while protecting nearby structure throughout the construction process. Now, I would like to explain the effectiveness of the piling and monitoring system throughout the projects. The slide indicates that the construction activity did not cause excessive ground movement or affect nearby structures. As shown in the outcome summary, the MRT infrastructure was fully protected throughout the piling works, with all movement remain below the alert threshold. The result also confirmed that the conservative construction approach, including the use of polymer slurry and more controlled drilling methods in MRT, which is sensitive areas, was effective in minimizing risk. In addition, the rod socket performance consistently meet the required design standard despite the varying limestone condition at the site. Overall, this result demonstrates that the selected construction method, quality control measure, and real-time monitoring system successfully ensure safe, stable, and high-quality piling works while protecting the surrounding environment and infrastructure. Now, for this slide, I will explain the cost of implementing the foundation protection measure for this project. The total foundation works are estimated to around 160 million and 200 million ringgit, which is accounts for approximately 9 to 11% of the total project cost. Out of this amount, around 12 million to 80 million ringgit is allocated for protecting the nearby MRT infrastructure. This additional investment cover the use of polymer slurry, specialist monitoring system, regular inspection, and independent engineering review to ensure construction is carried out safely. The cost of constructing pile also varies depending on the site condition. Under normal condition, piling costs range from about 2,500 to 4,500 ringgit per meter. However, in more challenging limestone ground or where large diameter piles are required, the cost increased to between 7,000 and 11,000 ringgit per meter. Overall, this protection measure increase the project cost. They are valuable investment because they improve safety, reduce construction risk, and protect the nearby MRT infrastructure. Now, I'm going to talk about some of the challenges encountered during the piling works and the action taken to overcome them. During construction, several technical issues can occur due to ground condition and the complexity of the project. To manage this challenge, the project team closely monitor the construction process and engineering solution. Whenever a problem was detected, work was reviewed immediately. Corrective action were implemented and construction continued only after safety was confirmed. This approach helped reduce risk, maintain construction quality, and protect nearby structures. Overall, effective problem solving, continuous monitoring, and quick decision making were essential in ensuring that the piling works were complete safely, efficiently, and according to the required standards. Now, I would like to present 4 ways to future-proof underground construction by improving safety, efficiency, and long-term performance. First of all, pre-demolition ground penetrating radar, which is GPR. GPR is used before excavation to detect underground utilities and hidden obstacles. This helps prevent damage, improve safety, and reduce construction delays. Secondly, mandated casing isolation, which is temporary steel casing are used to support the borehole during construction. After the work is complete, the casing are removed and replaced with recycled polymer slurry to protect the surrounding soil. Thirdly, foundation digital twin. A digital twin is a virtual model that monitors the foundation in real time. It helps engineers detect problems early and plan maintenance more effectively. Finally, geotechnical risk sharing. This involves clear agreements between all parties on how to manage unexpected ground conditions. It reduces dispute and helps the project run more smoothly. In summary, these 4 strategies make underground construction safe, more efficient, and more sustainable while improving the long-term performance of the project. Now, I would like to invite Muhammad Taufik Hidayat, who will be the next presenter.
Now, I will move on to the comparison between Merdeka 118 and Bukit Bintang City Centre. Merdeka 118 is a single super tall tower, so it requires much large bore piles, approximately 750 piles, reaching 80 meters and diameters of 2000 mm. In contrast, BBCC is a mixed-use development consisting of several towers and hotels. Therefore, it uses around 2,100 bore piles with varying diameter, depth up to 65 meters. For Merdeka 118, the main challenge was the presence of extreme cast cavities and nearby heritage buildings. Meanwhile, BBCC had to protect the adjacent MRT tunnel, which required continuous settlement monitoring throughout construction. Although the total foundation costs were different, both projects allocate around 8 to 12% of the total construction cost to foundation works. Overall, both projects achieved excellent foundation performance. Neither project experienced structural pile failure or post-construction foundation distress, showing that the selected foundation system were highly effective. For Merdeka 118, the high construction cost was necessary to support the enormous structural load of a super tall building built on challenging car limestone. For BPCC, the use of different pile size and careful monitoring of the MRT tunnel provide an efficient balance between safety and cost. This case study demonstrates that selecting the appropriate deep foundation system together with proper investigation, testing and quality control is essential for ensuring safe and successful construction on Kuala Lumpur limestone geology.
That's all from us. Thank you for your attention. Thank you.